Hello, my name is Nathan, and welcome to my talk about triangle detection in H3 graphs. This is a joint work with Amir Aboud and Ron Safir. So triangle detection is a graph problem where we are given an n-vertex graph G and have to decide whether G contains a triangle or not. It can be solved in cubic time by enumerating all triplets of vertices. It can also be solved using fast matrix multiplication. We compute the third power of the adjacency matrix and check if there is a non-zero entry in the diagonal. The reason why it works is because an entry corresponding to a vertex U contains the number of triangles incident at U. The running time is strongly subcubic, meaning that it runs in n to the constant where the constant is smaller than 3, specifically n to the power of 2.371, so on. But except for fast matrix multiplication, we don't know of any other algorithm running in strongly subcubic time. Well, people have tried to find such algorithms, and these algorithms are called combinatorial algorithms. It's not a rigorous mathematical definition. It works, but it works for us. We can identify a combinatorial algorithm when we see one. Okay. The fastest combinatorial algorithm currently is the one by Amir Aboud et al. From stock 24. It runs in n cube over 2 to the power of the 7th root of log n. It's still not strongly subcubic. And people use the following conjecture to prove hardness results. It's called the combinatorial triangle detection conjecture. It says that there is no such algorithm, no combinatorial algorithm running in strongly subcubic time. Why this conjecture is interesting? Well, falsifying it will give us a bunch of new hopes. First of all, it will give us a new approach to solve triangle detection in quadratic time, which will be linear in the size of the input for dense graphs. Fast matrix multiplication might also get to n square, but at the current pace, it doesn't look that it's going to happen soon. So maybe all we need is just a fresh new technique to tackle the problem. It will also give us hopes to solve other problems in much faster time than the current state. For example, all per shortest path is a problem that we don't know how to solve in strongly subcubic time, but it is reducible to a variant of triangle detection called the minimum weight triangle, where the edges of the graph are weighted, and we have to find the triangle of minimum total weight. Threesome is also a problem which is reducible to triangle listing, where given a parameter t, we have to list t triangles. And there's also other problems like OMV, online matrix vector multiplication, which hopefully will be able to solve using more combinatorial techniques than what we currently have. In this problem, we are given a matrix. We have to pre-process it, and so that given a vector, we need to compute the matrix, the product of the matrix and the vector efficiently. The problem is that fast matrix multiplication does not address this variant. It does not address weighted listing and online variants of triangle detection. So it will give us a new hope to tackle any of these variants. The main question in our paper is whether the conjecture holds when G has more structure. And the notion of structure that we use is the one of H3 graphs. We say that G is H3 if it does not contain H as a subgraph. For example, a complete bipartite graph is triangle free. It also contains subgraphs such as C4, C6, the even cycles. And let me emphasize, and the reason I'm saying it is to emphasize that we're only talking about subgraphs and not about induced subgraphs, which is another notion of H3ness. So the objective is as follows. We need to classify each pattern into one of the following classes. The first one, let's call it the easy class. These are the patterns for which triangle detection in H3 graphs is solvable in strongly subcubic time with a combinatorial algorithm. And the second class, we can think about it as the hard class, is all the patterns for which the problem remains at least as hard as in general graphs. Let's see some trivial examples. So if H is a node or an edge or even a triangle, then triangle detection in H3 graph is in constant time. There cannot be a triangle in the graph, so you just answer no. If H is a triangle with an attached edge, it means that if G contains a triangle, it must be an isolated component. So we just have to run a connected components algorithm in linear time and check for a component of size 3 that induces a triangle. And there's also, on the right side, we identify a class of graphs, of patterns, for which the problem remains hard. These are patterns that are not three-colorable, for example, K4. How do we prove such a result? It follows from a standard technique called color coding. Given a graph G, which is, think about it as an input to triangle detection, we can partition its vertices into 3 buckets randomly, to each vertex is assigned a bucket uniformly at random and independently. And then we delete edges within each bucket. So we get a 3-colored graph, G prime. And what is the promise about G prime? If G contains a triangle, G prime also contains a triangle with constant probability. It's the probability that each triangle vertex is assigned to a different bucket. But now G prime is H3 for every H which is not three-colorable, in particular K4. So we get the corollary that if H is not three-colorable, then the problem remains as hard as in general graphs. So if there was an algorithm solving it in strongly subcubic time, we could also solve general graphs in strongly subcubic time, and it would break the conjecture. Okay, so we know what happens when the coloring number is greater than 3. What if it's smaller than 3? These are bipartite patterns. Then we use a result from extremal combinatorics. It's called the Kovári-Sós-Turán theorem. It says, if H is bipartite, then in an H3 graph, there are few edges. There are subquadratic number of edges, strongly subquadratic number of edges. And then we can also solve triangle detection in strongly subcubic time, just by taking combinations of edges and vertices. So that's the current picture. We have trivial patterns and bipartite patterns like trees and even cycles on the left and the non-three colorable patterns on the right. So what happens to the rest of the patterns, to the 3 chromatic patterns, like 5 cycle? Do they go to the left or to the right? We managed to show that for a large class of patterns that have a spatial type of 3 coloring, so these are 3 colorable patterns, but they admit also a special type of 3 coloring, there is a strongly subcubic algorithm running in n to the 3 minus 1 over 2 to the k time. K is the number of vertices in H. In particular, it gives a complete classification for all patterns of size less than 9. And the picture looks like this. And this notion of special type of 3 coloring, these nicely colored patterns, it captures bipartite graphs and odd cycles and also funny looking patterns like the one in the middle. We will later see what is this coloring. But first we have to see some basic example that will provide us with the tools that we need. So our working example is an algorithm for 5 cycle free graphs. So suppose G is 5 cycle free, and we're going to have two cases depending on the degrees of the triangle vertices. For some threshold parameter delta, the low degree case is the one where a triangle contains a vertex of degree smaller than delta. We can check if a vertex of degree smaller than delta participates in a triangle in order of delta square time by taking every combination of its neighbors. And we can repeat this process, and each time, if we did not find a triangle, we can delete that vertex. If we did not find a triangle, we end up with the high degree case, where the vertices of the triangle, if it exists, they all have degrees at least delta. Then what we do is we sample small number n over delta vertices from G. Because of the high degree promise, with high probability, one of them will hit a neighborhood of the triangle. So because it's only a small number of vertices, we can check for each one if it participates in a triangle. It takes n squared time at most per vertex to check if it participates in a triangle, and there are n over delta sampled vertices, so for a total of n cube over delta. It's subcubic. If none of them participate in a triangle, we continue. We construct a ball of radius 2 around each sampled vertex. Again, okay, so what is this ball? It's just you look at the neighbors and then the neighbors of the neighbors. All the vertices at distance at most 2. But each ball can be as large as n squared. It might be the whole graph, and the graph might be dense. So again, it takes n cube over delta time to construct these balls. And because one of the sampled vertices, at least one, is a neighbor of the triangle is contained within one of the balls. And also, because we know that none of the sampled vertices participates in a triangle, then the first layers, the distance 1 layers, are all independent sets. So it must be that the triangle has one vertex at distance 1 and two vertices at distance 2. So we have to search for the triangle, but because each ball is large, potentially large, it will take n cube per ball. It's too much. We have to exploit 5 cycle freeness, and we do it in the following way. Consider an edge at distance 2, xy. Because it is at the distance 2 layer, then x and y, they have parents, z and w, to reach the root of the vertex. If these parents are distinct, it closes a 5 cycle together with the root. And if they are the same, it closes a triangle. So the key idea is that the existence of an edge in a 5 cycle free graph implies the existence of a triangle. So all we have to do, instead of spending n cube time per ball, is just to search for an edge at the distance 2 layer. And it takes only n squared time to do so. So in total, we get the running time of n delta square for low degree and n cube over delta for high degree. We can balance the terms at n to the 2/3 to get n to the 7 over 3. Let me just say that this algorithm is not an optimal algorithm for 5 cycle free graphs, but this example is important to us to get the general algorithm. So how can we generalize this algorithm to other patterns? It seems very tailored to 5 cycles. The idea is to use a recursive view of the algorithm. We started with a graph G, which was 5 cycle free. We cleaned up low degree vertices and constructed some random balls. And eventually we ended up with a search problem on a graph G prime, which has 2 layers. One is an independent set, distance 1, and the other one, the second layer is the vertices at distance 2. And G prime is free from a P4. P4 is the path on 4 vertices, which is like a sub pattern of 5 cycle when we remove a vertex. Well, it's not entirely true what I say. It applies only to P4s where the endpoints are in the distance 1 layer and the midpoints are in the distance 2 layer. So the recursion doesn't work. There could be many P4s in G prime. For example, on the right, you have zigzagging ones and P4s that they remain in the distance 2 layer. So what we wanted to have is a graph that is P4 free, and then we could continue the same approach. So the idea is to use a more general notion of H freeness. Because we reduced to a more general notion of freeness, we have to solve a more general notion of freeness. And we defined the following one. It's called colored H-free graphs, where both G and H are colored, but G does not contain a copy of H that preserves the colors. The colors of H are given. Here's a few examples, trivial ones. G and H are three-colored. H is an edge with red and blue endpoints. So G looks like this. It might have many edges, red and green, many green and blue edges, but no red-blue edges. And we can solve the triangle detection problem for this. It takes constant time. Of course, there is no triangle in such graph. Similarly, if we take H to be a two-path with different colors, with red in the middle, then each red vertex has either only green neighbors or only blue neighbors. It cannot have both. So again, there is no triangle in such a graph. We can solve it in constant time. But if we will take a two-path where the endpoints have the same color, say blue, it means that a red vertex can have at most one blue neighbor. So we can check if a red vertex participates in a triangle in order of n time. We just have to check combinations of blue versus green neighbors. And there is one blue neighbor and at most n green neighbors. So it takes in total n squared time for triangle detection in colored H-free graphs for this pattern. Now we will see that the recursive view from before actually works. So we want to solve the problem for 5-cycle free graphs. We start with a graph G that is 5-cycle free. We can color code G like before and end up with a subgraph of G, which is 3-colored, and is also 5-cycle free for the specific coloring where you have a red vertex with 2 blue neighbors and so on. Of course, it's free from it because if there was a copy of such 5-cycle, there was a 5-cycle in G as well. We can assume without loss of generality that all vertices have high degrees. We consider a more general notion of high degrees to color class. So it means the blue vertices have, for example, many red neighbors. And under this assumption, we can apply the same procedure as before. We can sample some red vertices and hit a neighbor of the blue triangle vertex. So we can sample a red neighbor of the blue triangle vertex. And what does it mean? It means that we can throw away all the non-neighbors of this red vertex. So we started with a graph G prime on the left and ended up with a graph G prime prime on the right. But since the graph on the left was 5-cycle free from this coloring that you see, the graph on the right is P4 free. For P4, where the 2 endpoints have the blue color, because such P4 would be completed together with the red vertex into a C5. Okay, so it works for 5 cycles. Now the question is what to do with more general patterns. So crucially, we needed to embed a vertex of H that has a monochromatic neighborhood, that all its neighbors have the same color. Say a red vertex that has only blue neighbors in H, then we can embed it and end up with a graph, subgraph, that is H minus V free, where V is that red vertex of H. But okay, so the question is which patterns have a coloring where there is always, we will need to always have a vertex with a monochromatic neighborhood. And what are the patterns that have such a coloring? 5 cycle is such a pattern, as we saw, but there are more patterns. We call it a degenerate coloring if every induced subgraph of H contains a vertex with a monochromatic neighborhood. So we have a small example here where there is a blue vertex with red neighbors. You delete it, you get red vertex with blue, blue vertex with green neighbors, green with red, and so on. And the main result is for for patterns that admitted the degenerate 3 coloring, for which we have a strongly subcubic algorithm. And the picture looks as follows. So we have the degenerately 3 colored patterns, or more precisely, the patterns that admit such coloring. We can find the coloring in constant 3 to the k time if we need. And on the right, we have the non-3 colorable patterns. Now the next thing to ask is what are the patterns that do not admit such a coloring? So here's the smallest unclassified pattern in our result. It has 9 vertices. It contains a triangle and a 6 cycle. And you can check for yourself that while it is 3 colored, there is no degenerate coloring. There will always, like, all the vertices will have neighbors in 2 colors. To summarize, while we did classify the patterns of size smaller than 9, we put on the following hypothesis that says that the problem in H3 graphs is easy for patterns that are 3 colorable and also contain at most 1 triangle. Now, I did not discuss this result about patterns that contain more than 2 triangles. We showed that if a pattern contains more than, or at least 2 triangles, for example, a diamond, then the problem remains hard. But due to lack of time and to stay focused, I did not discuss this. And the rest of the patterns are hard. Okay, so like, so just to say, it's an open question to refute or prove this hypothesis. More open questions are about other models. Do similar results hold in the congest model of computation? There is the question of improving the running time. We shave the n to the 1 over 2 to the k. Can we get 1 over poly k? Or can we get a conditional lower bound? That is non-trivial, that is not quadratic, not cubic. Okay, to get an exact running time, say. And also there is a question, this question is interesting given for non-combinatorial algorithms. If we allow fast matrix multiplication, can we, for example, get n square time? So that was it. We'll be happy to answer any questions if you have by email. Bye-bye.